So, hello everyone, and good morning, good evening, good night to everyone. And hello everyone. So, today is Tim Hamilton's second session, which is today on AGN spectroscopy. Since there are some of you all who are new to the course, please note that in the earlier playlist, that is the Discovery, the Astrosprint Enterprise set, you'll find the Agent Spectroscopy 1. Okay, that was the first one. And this is kind of a sequel to that. So in case you have some problems in understanding or in this thing, I would urge you all to see that video after the class, right? So please have a look at that video if there's anything not too clear. There's some newcomers over here. So this thing. And over to you, Tim. Yeah.
Okay, thank you, Priya. Good morning, everybody. And let's see, and with that, there, say the last change. I've been refining the talk as we were getting ready here this morning. For those of you who had been to my first session on the AGN spectroscopy, which was, boy, that was back in, hold on a second, when was that? Back in March.
So end of March.
Several months.
Yeah.
This is a follow-on to it. The first one had two things that I did. The first was I introduced the concept of spectroscopy and how we apply it to active galactic nuclei, or AGN, in particular quasars and sievert galaxies. Today, I'm going to be following on to that and be applying it again in a different way, where in the first one, I had shown you how to measure the masses of black holes by measuring the Doppler shifting of gas as it orbits the black hole, and just using, hang on a second, let me think here. Kepler, Kepler's orbital motion laws then. Tonight, sorry, it's overnight for me. This morning, I'm going to be showing you how to use the Sloan Digital Sky Survey archives, where you don't have to do the line profiles yourself. You can use what they've already measured for you, and how to do what's called a SQL database query in order to download, or you could download tens of thousands of galaxy spectra and to analyze them actually very quickly. We're going to be using a diagnostic diagram called the BPT diagram, which I'll show you how to use in order to distinguish certain kinds of active galaxies from others. And then I'll wrap that up with a project where you can look for differences among those over cosmological time, over billions of years of evolution. All right, so let me start here and pull up my program. Oh, that's the last change. There we go. All right, now screen sharing. Okay, can everybody see the title screen here?
Yes, we can see it, all fine.
Okay, thank you. All right, so what I'm showing here it's actually the same title slide that I had before, but this is showing the spectrum of thousands of active galaxies done with the Sloan Digital Sky Survey. On the horizontal axis, we have the wavelength starting at 3,600 angstroms in the near ultraviolet, and going all the way out through the near infrared out to 10,400 angstroms. This is with the BOSS, B-O-S-S, baryonic oscillation, maybe sky survey, but I don't remember what the SS stands for. So from the near ultraviolet down to the near infrared. And the vertical axis is redshift, from 0, which is local, all the way out to beyond a redshift of 3, which is getting pretty far out there, billions of light years away. And what you see is with this false color image, the bright areas, the lighter colored areas, are emission lines, and the darker areas are a continuum. And you're seeing the effect, each row is a different active galaxy spectrum. And you're seeing, as they just stack these up here, the effects of redshift. As here's an, what is this here? This is a magnesium 2, that is singly ionized magnesium line. And you can see that going out here, and how as you get out to higher redshifts, it gets farther and farther to the red. Notice the kinks in these, and that's not because of some cosmic effect. It's actually because they have more at certain ranges of redshifts and fewer of them they find at different redshifts. So this is not a linear scale of redshift going vertically. All right, but over here we have hydrogen alpha, beta, and gamma, the first 3 of the Balmer lines, which are going to be some of our most important emission lines there for these galaxies. All right, a little bit of a review from last time. The spectroscopic notation we use in astronomy. First of all, we're going to be using angstroms, 10 to the minus 10th meters, for the measure of wavelength, rather than using nanometers. And the reason is because we're going to be looking at distinctions down in the single angstrom, the single digit angstrom difference, and sometimes even down to tenths of angstroms. And so nanometers is just a little less convenient. All right. We have the Balmer lines. These are what we call broad lines or permitted lines. They are permitted under the rules of quantum mechanics that allow an electron to make a transition down to, let's see, the Balmer line is where the electron drops down to the first excited state of the hydrogen atom or of a hydrogen-like atom. Specifically, we'll be looking at those of hydrogen. So H alpha, alpha is the 3 to 2 transition, beta is the 4 to 2 transition, gamma 5 to 2, and so on like that. We can specify their wavelengths here, lambda with the subscript of H alpha, H beta, and so on. And you see H alpha is in the red region of the spectrum, H beta is in the greenish part of the spectrum there. Gamma, we get on into the blue, and delta, we've gotten down to run into the near ultraviolet, and they start to get closer and closer together up to what's called the Balmer limit in the ultraviolet. All right, now, because these Balmer lines are permitted, that is, quantum mechanics has no prohibition on an electron making that transition, then they are very easy for an electron to do. They're very common. On the other hand, we have what are called the forbidden lines. Now, they're not absolutely forbidden by quantum mechanics, but in the first run through the rules of quantum mechanics that you do in a quantum mechanics class, you will see that they are prohibited by the rules of conservation of angular momentum. So the electron can't make a transition on these particular, that would produce these particular lines. And yet, we see these emission lines. Why is that? Well, they are permitted under other rules of quantum mechanics. It's just that these exceptions to them are rare. And by being rare, it means it happens less frequently. It takes longer for the electron to make that transition. It gets hung up there in an upper state for a while before it can transition to the lower state. Now, if we try to get the atoms in these states here on Earth in the laboratory, we need to have a very low pressure gas. And it turns out that even at the lowest pressures that we can create in the laboratory, we don't see these lines. So we never knew of them before until we saw them in space. The reason is that even the best vacuum we can produce on the Earth still has enough gas pressure that as the electron is sitting up here at this upper level, waiting for some random quantum fluctuation to let it drop to the lower level, in the meantime, another atom is likely to smack into it. And that collisionally excites the electron and makes it fall back down in a different way, skipping this transition entirely. So for these forbidden lines, then, we will have brackets around the element name, square brackets like you see here. The first thing we put in the brackets is the species of element. So O for oxygen, N for nitrogen. The next thing we use is Roman numerals telling us the ionization state. Roman numeral 1 is neutral. So H1, for example, would be neutral hydrogen. 2 is 1 electron removed. So H2 is ionized hydrogen. Of course, we can't remove any more electrons from hydrogen. It only has 1 electron anyway. But say with oxygen, we can have 2 electrons removed. That would be O3, and so on down the road like that. So O3 there, that is doubly ionized oxygen. But an atom, an ion here, can have all kinds of emission lines, not just one. So we need to specify which wavelength is the line that we're looking at. So we put lambda and then the wavelength in angstroms after it there. This O3 5007 angstrom line of oxygen 3 is a particularly bright one in active galaxies and nebulas as well. And it's a green line there. This was originally called nebulium when it was discovered in astronomical spectra before they figured out that it was simply an ionized state of oxygen. The N2 line, 6563, you'll notice that it's very similar in wavelength to the hydrogen alpha line, 6565 angstroms, and so that's a red line there. In fact, they kind of overlap. All right, so that's our notation. If it's in brackets, it's a forbidden line, and if it's a forbidden line, then it can't be created in a high density gas or high pressure gas, and therefore it's got to be in a thinner part of the gas cloud surrounding the black hole of the active galaxy. And so it's going to be farther from the black hole. Now, the distance from the black hole, as I told you last time, determines the Doppler shifting that we get. If this is the black hole, if you see my face here on the camera, my fist is the black hole, and we've got a gas cloud that's close by, Kepler's laws of orbital motion say it'll orbit very quickly. Now, we don't see that individual cloud. We see all kinds of clouds around here at the same distance, some moving towards us, some moving away. Those moving towards us are blue shifted. Those moving away are red shifted. I know this is review for most of you, but bear with me. So that means is that for gas clouds that are emitting lines close to the black hole, we see a large range of Doppler shifts. And therefore, because those are all blended together, we see a broad line. Only the permitted lines will make broad lines, because the forbidden lines can't be emitted in the dense cloud close to the black hole. They have to be emitted in thin, low pressure, low density clouds farther from the black hole, where just the gas is thinned out there. Because they're farther from the black hole, Kepler's law of orbital motion says they're moving more slowly. Because they're moving more slowly, the Doppler shifting is less, and we get a thin, narrow line. So, but I should note that the broad lines, the permitted lines are also emitted farther from the black hole as well. They can be emitted close or farther away. It makes no difference. They can do both. So the permitted lines tend to have both a broad component and sometimes a narrow component on top of it. Okay, going on from that. There we go. A typical active galaxy spectrum. This is, let's see here, this is actually a composite of many hundreds or maybe thousands of spectra. Would look something like this. Here we go from the ultraviolet at 1,000 angstroms, up through the visible, starting around 4,000, and on out through the near infrared at 8,000 there. So here you see the composite spectrum. I'm going to take a look at what they call the first eigenspectrum. That's a way of doing certain kind of data reduction. But right now, this particular one is pretty close to being the average spectrum here. And it's labeled, which is convenient. So here in the red, we see hydrogen alpha, and you see a very broad line, but you see a sharp peak on the top. That's that narrow component of it sticking up above it. The little hiccup over down and to the right is the nitrogen 2 line, which I told you is very close and tends to be blended with the H alpha. Over here, and we don't have it labeled separately. Over here, we have oxygen 3. We've got 2 lines there. While the bright one is the 5007 angstrom line. 5007, yes, angstrom line. And the other one, I forget its exact wavelength, it's 4,900 angstroms something. Notice that that tends to blend a little bit with the H beta. And there you see the broad component with the wide wings, and then a sharp peak on the top, which is the narrow component. H gamma here, mostly broad in that case. And then we have probably that's another Balmer line, and then they kind of get fainter and fainter. The lower, the alpha levels on the permitted lines tend to be the brightest because they require the least energy to do. Okay, then we have some magnesium 2, a broad permitted line there. We have a partially semi-forbidden line with a single bracket. I'm not going to get into that because, to tell you the truth, I'm not a spectroscopist and I don't understand all the rules on it. Another semi-permitted line. And here we have Lyman alpha, maybe definitely the most important of the ultraviolet lines there, and a very bright one. Okay, that is the 2-to-1 transition in hydrogen, the Lyman series alpha. Okay, so some of what the typical lines are like. Now, notice this, and this is going to be important later. It will be on the test. H alpha and the nitrogen 2 line here are very close together, in fact, blended. So they're almost the same wavelength. O3, 5007 angstroms, and the H beta are also very close together, not as much blended, but they're in the same region of the spectrum. And that's going to be something useful that we'll exploit in a minute. There we go. Okay, and here's what I was telling you about the broad and the narrow lines. So if we take here, this is H alpha, sharp peak, probably a nitrogen 2 on the shoulder there. Here we have O3, a couple of those lines, and H beta. We can decompose these if you take your proper software, and I showed you a little bit on how to do that last time, so that you have individual models, a Gaussian or a Lorentzian, and then there's also the Voigt profile. All of these are line profiles that you can do a fit to. And that is relatively straightforward, but you're going to kind of play around with the parameters. And then here we have H alpha with both a broad in blue and a narrow component in green. Actually, sorry, the narrow is in red, and then the green is the sum of the two. And then there's nitrogen 2 right there. Okay. Structure of the active galactic nucleus. We have here at the center the black hole in black appropriately, with a little pink accretion disk orbiting around it. That's the gas which is accreting or sticking onto the black hole. Now we have a cutaway showing the dust disk, the torus, which just means a ring, donut shape, which blocks our view of the accretion disk if we're viewing it from the side. It's also the source of a lot of infrared light. We have the broad line emitting clouds, the little gray clouds close to the black hole, orbiting in all directions. Some possibility of a bit of flattening of that with an overall direction of rotation, but we're not entirely sure. And then farther away, we would have the distant clouds, which are emitting narrow emission lines. And then in about maybe 10% of cases, we have plasma jets, which emit radio waves. Okay, now, you're not going to need to do the measurements yourself this time. What you are going to use, I want you to understand though, this is the concept of the equivalent width of a spectral line. Let's say that we have a very flat spectrum here. Here's the continuum with the dashed line on the left. And then we get to an absorption line, which is typical for stellar spectra, much less so for AGN. This is our starting point. Stellar spectra where we began in spectroscopy anyway. And let's say we have an absorption line, and here the line dips down at a certain wavelength, and then it comes back up. Okay, just a Gaussian profile line. Now, if we were to add up the area between the line profile and the continuum, that area would be the flux of absorbed light by that line, the total flux of the line. Now, of course, it's absorbed, not emitted, but it tells you what flux of light was absorbed by the line there. Okay, now, you could measure that flux in flux units. But a very convenient method is to measure the flux in what's called the equivalent width. And that is, if we scale the intensity, we normalize it so that the continuum is at a value of 1, and the bottom is, well, 0. 0 is 0, that's easy enough. Then, so we got that normalized. We don't need to, but to get the units to work out in a simple way, it's helpful. What we do is we draw a rectangle which has the same area as our line does between the continuum and the spectrum. And but we draw this rectangle so it has the same area, but it goes from the continuum level all the way to 0. See, our line profile may not actually go all the way to 0. It may not be fully absorbed. Most of them are. But if we draw a line that does go all the way to 0 and it's a pure rectangle, well, the height is 1. We go from 0 to 1. And the width is the equivalent width. So the equivalent width of a line, of an absorption line, is the width of a rectangle that has the same area of our line, but it goes all the way down to 0 level. And that equivalent width, we use W for width, and then lambda marks the wavelength where we are. Okay, now for an absorption line, the equivalent width is, of course, a positive number because it's dipping below the line, and the line is dipping below, the rectangle here dips below the continuum, and the absorption line dips below the continuum. So they have the same sign, and our equivalent width is positive. Now, this was all developed by the stellar spectroscopists and their absorption lines, but we, in the active galaxy community, need to do, it's convenient to use something like this, but we've almost exclusively got emission lines. So how do we deal with that? Well, let's normalize the intensity again so that 0 is 0 and the continuum is at a level of 1. Then we've got our emission line here, drawn somewhat more irregularly, and we can draw that rectangle again going below the continuum. So yes, we've got an emission line, but our equivalent width is for a rectangle that drops down all the way to 0 once again, because if we went up, how far up would we go? You could say, well, up to the peak, right? I mean, that would make some sense. However, how high up that peak goes in flux density, because we're scaling this, we're drawing our spectrum as flux density per unit wavelength. And if we have better spectral resolution, that peak is going to go higher. If we have lower spectral resolution, our instruments aren't as good, the peak will be lower, even though the total flux would be the same. It would just broaden it out there. So we can't do it that way. We've got to be consistent. So again, we go from the continuum level, which is 1 here, all the way down to 0. In this case, the equivalent width for our emission line will be negative because the actual line goes up and the equivalent rectangle goes down. They have opposite signs. Now, this has drawn in there. I didn't draw this myself, but it's useful to see. A little caveat here, something to pay attention to. You see, another thing that we can measure about spectral lines is the full width at half maximum, and we've done that last time. FWHN. So you go from 0 up to the peak here, and then you measure how wide it is when you're at halfway up to the peak. Okay, now that's a measure of the width of the line. If you're looking at the Doppler shifting, then that's an important thing. But we're not looking at the width of the line here. The equivalent width is not a measure of the actual line width. It's a measure of the actual line's flux. Okay, so keep that distinction in mind. Okay, so what we're going to do now is, let's say that we've got equivalent widths for a number of these lines, such as O3, 5,007 angstroms, nitrogen 2, 65, 60, I forget exactly which, 65, 61, something like that. and say H alpha and H beta. So let's say we can measure those. That's all conveniently in the yellow to red part of the spectrum. All right. What can we do with that? Well, a few years ago, back 1980, 40 years ago now, my goodness, Baldwin, Phillips, and Turlevich had written a paper in which they noticed that you could, well, if you're looking at spectral lines, just doing the spectroscopy alone, and you take a spectrum of a lot of galaxies, you'll find that there are a lot of galaxies that have stars, bright stars going on, newly formed stars, star bursts going on, where the hot star light, the light from the hot stars is ionizing gas around it there. And so you are making emission line regions. Okay, you get those, and you get these same kinds of lines that you see in an active galaxy, but you would like to distinguish between those emission line, those star-powered galaxies and the black hole-powered galaxies, the active galaxies. So what do? Well, they found that it was not possible to look at lines or line ratios by themselves, by any single line ratio. You could not distinguish between them very clearly. There was too much overlap. And what they found was that if you looked at two pairs of line ratios, you could distinguish them. So here's the original version of the so-called BPT diagram, Baldwin, Phillips, and Turlevich. It's a diagnostic plot, kind of like the Hertzsprung-Russell diagram is for looking at different classes of stars. This is for looking at different classes of active galaxies. Now, on the horizontal axis, you plot nitrogen. Let me be clear here. The equivalent width of the nitrogen 2 line at 6583 divided by the equivalent width of the H alpha line at 6563. Okay. The vertical axis, you take the ratio of the equivalent widths of the O3 5007 angstrom line to H beta, which is at 4861. Now, notice that we have logarithmic plots on both axes. Later, we'll find it's just easier to go in and take the logarithm, and then we can plot that numerically on a regular plot. Okay, then what you see here is all the galaxies that have circles are powered by H2 regions, that is ionized hydrogen gas, generally coming off of hot stars or being ionized by hot stars. Whereas all of these, which are circles or filled circles or black diamonds, are active galaxies. We've got two different kinds that we have there that we'll get to in a little bit. Okay, so this is a standard diagnostic diagram that we use today in order to distinguish active galaxies from star-forming galaxies. Now, these have been updated in the years and the decades since. The biggest advance that I'm aware of is by Lisa Culley, 2006, or this is her 2006 paper. And this comes right out of her PhD dissertation. She fantastic work here. She is really, I still think, probably the leader of this field. And so Culley 2006, Culley et al. I forget the other authors right now, but I will show you the paper. And she had done more work in using the Sloan Digital Sky Survey, which I'll have you using, and finding very precise dividing lines between the different classes here. So if we plot O3 versus H beta for the vertical axis, and notice now we're taking the logarithm first and we're plotting it on a Cartesian plot. And we compare that to the logarithm of N2 over H alpha, same one that we had before. She shows that you can separate the active galaxies, kind of looks like a butterfly here. Active galaxies are in this branch in the upper right. H2 region galaxies form this curve here at lower left. And what you have is composites that have a bit of each are in between these two lines here. Okay, now, if you only separate out the AGN from the H2s, and you don't worry about the composites now, then if you plot O3 versus H beta, O3 over H beta versus S2, now we've got sulfur involved, over H alpha. right? A different line. We get a better separation between two different kinds of AGN, which are called sievert galaxies and liner galaxies. I'll explain what the liners are in just a moment and what a sievert is. Okay, but third, the best separation between these two different kinds of active galaxies is if we plot for the vertical axis stays the same for all of them. The horizontal axis is singly ionized oxygen. And I'll tell you which line in a minute when we get to that. Okay. Now, how do we, before I explain what these are, why do we choose these lines over others? In fact, I didn't really even explain it for the first diagram, the original BPT diagram. You see, if you take a look at the wavelengths, you notice that the O3 and the H beta here, 5007 angstroms and 4861, they're in the same part of the spectrum. They're both in that middle green-yellow region there. And if you look down here at the horizontal axis, 6583 and 6563, those are very close together. The reason for choosing those is that these pairs is that by being in the same part of the spectrum, they are not, they are affected by dust in the same way. So dust is a problem in a lot of astronomy. I've got a colleague who has spent her whole career looking at dust and making models for it. And dust will tend to redden the light that passes through it because it will scatter short wavelengths, bluer light, and it will let through the longer wavelengths or the redder light. So it dims the spectrum in the bluer end, and it doesn't affect it as much in the redder and the infrared ends. So if you were making a ratio of say, let's say that we were taking a look at H beta to H alpha. H beta is much redder, much bluer than the H alpha is. We'd be comparing lines at different ends of the spectrum, different parts of the spectrum, and the H beta would be more affected by dust than the H alpha would be. We would not be able to tell whether a low level of H beta relative to H alpha was due to intrinsic differences or if it was simply due to dust in this galaxy. The dust could be inside that galaxy, or it could be in our galaxy, although at least there we have some decent maps of it. So dust is largely an unpredictable effect. I mean, we know how it works, but we don't know how much dust there really is. Okay, so you want to compare lines that are in the same part of the spectrum. That way, if you don't know how to account for the dust, which when you're doing this, generally you will not, then it doesn't matter all that much. Okay, so that O3 and the H beta lines will both be more affected by dust than N2 and H alpha, but because we're taking a ratio of them, they're affected pretty much equally, and the effects of dust go away. So that's the great thing about this. Now, the next thing to notice is in each one of these axes, you've got your pair is a narrow line divided by a broad line, a forbidden line divided by the equivalent width of a permitted line. So how do we interpret this? The O3 to H beta, the vertical axis here, is, let's see here. It is mainly looking at the average level of the ionization and the temperature of the gas there. Now, the temperature, you understand that easily enough. The ionization, however, is how strongly ionized are the atoms that make this up. So let's see here, we got a question from Ankur. Can we apply some sort of virial factor which would account for the effects of dust in this analysis? With virial, I'm thinking of dynamics there. If you might want to elaborate on that, I might think about it a little bit more. But with the dust, it's not a dynamics issue. It goes into the formation history and the evolution of the galaxy. And so some cases you've got more star formation that goes on, and so you get more dust, you get more evolved stars and such, and in others you have less of it. And that makes it tough to do. Unless we look at a template, if we have a complete spectrum of the galaxy, we may be able to, as we would say, shoehorn it into a template where it's we choose this most similar other galaxy that it's like, and we assume that it's got the same amount of dust. And I've done that before, and I've never really been all that satisfied with the results, honestly. So yeah, dust is tricky. If we can avoid it, I like to avoid it. Okay, now the vertical axis then is a combination of temperature and ionization level. How strongly ionized is the gas? And that tells you what we would say, how hard the spectrum is as well, and how intense that is of the ionizing radiation. The second one, though, the horizontal axis, I will quote from the what's called the AGN squared book. This is a useful book if you're doing spectroscopy. This is in the camera here. The Astrophysics of Gaseous Nebulae and Active Galactic Nuclei by Donald Osterbrock and Gary Furland. And this is a really standard book on this here. AGN, both of the phrases there. To quote from them, it says, "It's not very clear how we can interpret the horizontal axis. It just works in separating them." I think that the BP and T were all kind of experimenting around until they found something that worked there. I will note, though, that there's another version, that middle one that I showed you, where you use O1 and sulfur 2 lines relative to H alpha. And in this case, you're looking at the relative importance of the partially ionized zones produced by high energy ionizing radiation. Okay, and again, not being a spectroscopist, I'm not quite sure how to visualize that, but it's where you don't fully, I guess I did know about that there. It's where you don't fully ionize it, that radiation gets absorbed as it ionizes some regions, and as it goes farther out there, you don't have enough to keep ionizing it farther out. Okay, but anyway, that N2 can't really interpret physically. We just accept it for what it does. Okay. Now, to separate active galaxies from H2 and from composite objects, we want to use this O3 against N2 plot. But if we want to separate different kinds of AGN like sieverts and liners, we would use the O3 versus O1 plot here. So you use a combination of both of these. Do your first cut to get only AGN, maybe to get rid of the composites with your first plot. And then when you want to do your separation of sieverts and liners, you put them on the second plot there. Actually, I'm not sure if you need to throw things away from that, using that first plot there. But if you want to find composites, then you can't do it with this third one. Okay. Sorry, I should say, what is a liner? Now, what is a sievert? Sievert galaxies are basically like low-powered quasars. They are simply, to tell you the truth, really the only physical distinction we make between a sievert galaxy and a quasar is that the sievert is dimmer, intrinsically less luminous. There's a cutoff, anything with a B or V band magnitude brighter than -23, absolute magnitude, would be considered a quasar. Fainter than -23 would be considered a sievert. And even then, I see galaxies which are on one side of the line or the other, and you've got papers that call them the opposite thing, because there's not that much physical distinction between them, except at the extreme ends. Now, so the spectrum I've already shown you here is, I think that is a sievert spectrum, or if it's a quasar spectrum, same difference really. The liners, though, are interesting. LINER is an acronym. It stands for Low Ionization Nuclear Emission Region. And when these were first found, well, low ionization means that you get the spectral lines that you get are mostly by those ions which are either neutral, which is not ionized at all, or they're singly ionized, and they're atoms that don't require a lot of energy to pop that outer electron off. So neutral oxygen, neutral hydrogen for that matter. Singly ionized oxygen, singly ionized nitrogen, singly ionized sulfur. Those are your big ones for that there. And the contrast with that would be strongly ionized atoms like doubly ionized oxygen, doubly ionized neon, singly ionized helium. It takes a lot more energy to pop off the second electron on the helium atom. And so that's right in the first. And so anyway, that's a more strongly ionized atom. So low ionization, so your former category, nuclear emission regions. So it's emitting those spectral lines from the nucleus of the galaxy, like you would with a quasar or Sievert galaxy, an active galactic nucleus. But originally, when they first found them a few decades ago, it was speculated that liners might not really be active galaxies. It may be that liners were being powered by stars, strong star formation, rather than from a black hole. And after a few decades of looking at them, they have pretty much concluded that there's no evidence that they are powered by stars. They are, in fact, true AGN, and they are indeed the lower, they tend to be fainter, less powerful than Sievert galaxies, and Sieverts are less powerful and fainter than quasars. So liners are down at the extreme faint end of that distribution. Okay, so I will make one more note on a modern BPT diagram. Lisa Culley, in her 2006 paper, finds a version of one of these diagnostic diagrams, which gives it is the simplest division lines, and it gives the best separation between the Sieverts and the liners, and for that matter, the H2 regions here, although not H2 in composites. And what you see, and by the way, every dot here, I don't know if I explained that clearly, every dot here is an individual galaxy. So you make these two, you've got an X and a Y, so you've got your coordinates there for your line ratios. So if you take the logarithm of the O3 to the O2 lines, see here, we're not even using the, we're not doing it relative to H beta for the vertical axis, versus O1 to H alpha for the horizontal. Then what you find is you get this nice, perfectly straight diagonal line to separate the AGN from the H2 regions. And then we get another nice, perfectly straight line separating the Sieverts very cleanly from the liners. I say very cleanly, but the liners are in red. You see there is a little bit of overlap with the Sieverts. The Sieverts are black, and there's a little bit of overlap into the liner area. So none of these diagnostic lines are perfect, but they're really pretty good. And then we get still a nice separation of H2 regions from these here, from the AGN. Now, a caveat about this version here is that O3 and the O3 and O2 lines are in different parts of the spectrum. Remember what that means? It means unless you know how to account for the dust, you shouldn't use that because it's differences in intrinsic dust are going to cause you very large problems. They're going to produce a lot of scatter. That takes a lot of work in order to fit a dust model to these things. However, if you had that, this would be a nice, neat division here. Okay. Now, let me see here. Let me make sure I've covered all of the points on this. I believe I have. So we're going to go on to the live part of the demonstration. Okay. Now, we're going to go on to, let's see here. I need to pull up my web browser. Oh, first, this is Lisa Culley's 2006 paper. I put it in here so that you can, I'll type it into the chat window as well. Culley et al. 2006. Monthly Notices of the Royal Astronomical Society, Volume 3, 72, page 961. Okay, definitely worth looking up for doing this. It's practically a step-by-step guide for doing the separating them into different classes. And I'm going to be using her division lines between these in order to show you what we're doing now. Okay. So I'll show you what I have done. I've already finished first. All right. I have downloaded, I guess I put 1,000 galaxies from the Sloan Digital Sky Survey on here. And I have taken their line ratios and I've made both of these plots. That is Culley's first and third plots here. So A and C. All right. So for plot A, we have the separation between, on the lower left, are the H2 region galaxies. In the middle wedge here, we have the composites, and up and to the right of the green curve, we have the AGN. Both the sieverts, which are more or less in the upper region, and the liners, which are more or less in the lower right. Then if we plot O3 versus H alpha, O3 divided by H alpha versus O1 divided by H beta. You know what? I turned that around, didn't I? Hang on here. H beta is always in the vertical axis and H alpha always in the horizontal axis. Okay. Now with that in mind there, and in here on the right-hand graph, that is graph C, and with the same data points, the same galaxies. I have my H2 regions and composites mixed in here, my sievert galaxies up here, and my liners over here. So I'll show you the equations and how to do the divisions. Oh, hang on a second here. I should put up on PowerPoint. There we go. All right, I put this out of order, but this here, let's put it on this. This gives you the four equations that you need in order to do the separation. Now, this is taken straight from Culley's paper. She writes it in a way which I'd say is maybe just a little bit more complicated. She puts it in which group is in which region. And so she tells you, well, your y-axis is, your y value is greater than this function here, or less than, or the x is greater than this, or less than this. But I just prefer to draw the lines, and then you can see where they are. Okay, there are three lines here. One of them is put on two different plots. The first one is the KE. And the truth, I never did quite find out what that stands for. It kind of makes me think of Culley, but the O3 line and the O1 line, those might even be publication years. So, and then a sievert liner division line. So the KE3 line gives us a separation between, hang on here. I have to draw that separately. All right. I tell you, so on the left-hand side below each one of these line labels, I tell you which the X and the Y axes are. And then finally the sievert liner one here. So the first two are for plotting that O3 over H beta versus N2 over H alpha line plot. And these two lines are going to be drawn on it. KE1 is going to be our line that goes farther up and to the right, and KE3 is goes farther down. And these two lines separate. Between them are the composite regions. Now, for the separating sieverts and liners, we take KE1, but we've got a slightly different equation because it's different variables. And then we also draw the sievert liner line here. So KE3 is the blue dashed line, KE1 is red in each case. And then up here, that sievert liner division line is this one here, like that. I will say that she says to truncate it a little bit too far over to the right, unless I've just misunderstood her, but it looks like on her own plot, she brings it right down until it touches that red line there. Okay. Now, how do we get these data here? I've drawn out in each case, this is N2 divided by H alpha, O3 divided by H beta, and O1 divided by H alpha there. Okay, assuming that I wrote that correctly now. Yeah. All right. And we've got other things about each galaxy: object identification, right ascension declination, redshift, and a few others I'm going to show you. Okay, now let's see. I've gone on for just about an hour, so I should not run my mouth too much longer. Let me get the right plot here, on the right page here. Okay, where I want you to go to get the data is the Sloan Digital Sky Survey. Putting it in the chat window. If you go to just sdss.org, you get the latest data release, which right now is data release. So data set 16. So it's the 16th time they've released their set of data. And honestly, the easiest way to do this is to go to data in their education page, or Sky Server, the Sky Server page. We're going to go down here, accessing the data, Sky Server. It's the most user-friendly. Yes, it clearly was developed several years ago for smaller computer screens than we have these days, but it still works. All right, data access. And we're going to go to an SQL search. Now, SQL is, I don't even remember what it stands for. It's a computer language, though, and it allows you to query a database. They have a tutorial for SQL. Actually, this is more of a reference guide here. If you go to, let's see, I found the reference page for you. Let's see here. So I'm going to put into the chat window the tutorial, and I recommend just going through the tutorial. But I'll explain to you the kinds of things that that you're going to need. All right, SQL. Every SQL program or search has 3 sections to it. Double dash means a comment line. So all of these here are comments. This is just a default one they put in to let you see. The first section is called select. That says, what data do you want it to send to you? Okay, so this is a list of variables here. And you're going to get a table that comes back. Where each row is a single item in the database, and then each column is a certain variable, whatever variables you want it to bring back. I'll explain what those are in a moment. From, the next section is from. Which part of the database do you want it to search? A very simple database might only have one table in it, one underlying data table. This one has many different data tables and even more complex things they call views. A view is kind of a virtual table where it takes a little bit from this table and a little bit from that one and puts them together and so on, for convenience sake. And so you can search any one of those. This is a table called, really a few, but called photo objects, meaning the photometry measurements of these objects. The last section is called where. This puts in conditions for it. So you can specify a range where the U, that's the U band magnitude, is between 0 and 19.6, and G, the green magnitude, is between 0 and 20, for example. All right. Now, what I have written up for you here, found one that works. And you can modify this. In fact, you should modify this for your own purposes. All right. I don't want this to look too intimidating. only a little bit long because I've written it out to get everything that we would need here. Okay, so the first part, and capitalization is not important. Select top 100. That top 100 means it's only going to give you the first 100 of objects it finds that match the criteria that you got down in the where state. If you want to get more, honestly, probably you'll want to do like 1,000 or maybe do 10,000 or something like that. The only thing is that I don't know, you won't know how it sorts the top ones of that. It's just the first ones that it comes to imagine. But if you want to experiment with it first, just do the top 100 for a manageable size, and then you expand it to 1,000. If you leave off the top part there, you just say select, maybe you get 50,000 objects or something like that. And it may take a long time for it to give you the data. All right, here's what we want it to do. Each of these lines is going to be another variable it returns. The base 10 logarithm, that's log 10, of, parentheses, the nitrogen 2 equivalent width for the 6584 emission line. I think we said 6583 before. Could be that we're looking at vacuum equivalent wavelengths or in the atmosphere, and the presence of the atmosphere shifts the peak of the line by a little bit. And Sloan, I forget which one they use here, but okay. And I wanted to go in and divide that equivalent width by the H alpha equivalent width. And this is a variable name. It's one of their variables in the tables there. And I'm going to have it rename when it takes the logarithm of that ratio. I want it to just name that into. But I know it means that ratio. Comma, next variable. I do the log 10 of O3 divided by H beta. I'll call that O3. And the third beta I want back. I take the logarithm of O1 divided by H alpha. I call that O1. All right, the next thing. For any of you who have programmed in an object-oriented language, like Python or C++ and things like that, you'll be a little more familiar with this kind of notation. I guess even basic C probably has that as well. This is where we want the variable called object ID. It's going to identify the object so that you can look it up later and maybe look at a picture of it. And because that object ID could be appearing in several different tables that we're searching, I wanted to use the one in the photometric table, which I've labeled as P. So photometric, see down here in from, photo objects, that's a table. I'm going to call it P, and then in P, I want it to look at the object ID and give me that. Also, I want the right ascension, the declination, the redshift, Z, the model fitted magnitude in the red filter, R, and I want it to give me the error in that magnitude, and that's from the photometric table. S dot Z means the spectroscopic table, and the redshift it has there. The photometric one just doesn't have it, if I remember. Okay, and I don't put a comma after the last one. From, where do I search? I needed to make use of 3 different tables here. Spectrum objects, call it, we'll just abbreviate it S for simplicity. The galaxy spectral line data table, G, that's where we get these, into equivalent widths and things like that. And finally, the photometric objects, we'll call it P, and no comma after the last one. Finally, the conditions, which ones should I have it send back? Where the, what's called the best object ID in the spectroscopic table is equal to the photometric table's object ID. I started to put a comment here, but didn't get to it. This is how it's going to do what's called a join between 2 tables, where we're going to make sure that when we list all the criteria that this has to match up, we also list them in the same order between the different tables. Otherwise, we'd be dividing, one variable of, the H alpha for one galaxy, but we might be dividing it by the taking the ratio with N2 for a completely different galaxy. So we've got to make them match up, and that's how we do it there. And so each one of these is adding a required condition. where the spectral class is listed, it automatically categorizes it as a quasar, QSO, or as a galaxy. We don't need to be looking at stars for this. Next, the spectral object ID has to be the same in these other two tables, spectral and galaxy line. Make sure we're looking at the same thing for each one. Let's see here, next thing, the H alpha equivalent width cannot be equal to 0. Exclamation point equals means is not equal to. And that prevents us from getting a division error if we were to divide by 0. Same thing for H beta, because it's in the denominator over here. The next three make sure that the ratio is not 0, because even the numerator, we don't want it to be 0 either. If it were 0, we couldn't take the logarithm, and we get an error as well. By the way, it took me a few tries before I figured out that I had to put that in there. The final two things, I have put in a condition, which you will change, that the redshift Z is greater than 0.1 and less than 0.2. That gets us a fairly narrow range of redshifts. As you get to lower and lower redshifts, you should make the range be narrower so that the range of distances is fairly small. Remember that redshift and distance are not proportional exactly. Okay, so we do that. Now let's just you select your output format. If you're only doing 100 of them, you can get a quick look to make sure this query works by doing HTML. I submit my query. It says your SQL command was the following. We'll confirm that, yep, that's what I put in. Query output, it can only give you 500,000 if you do it in HTML. And look, we got into 0301, object ID, right ascension declination Z, magnitude and magnitude error. There's the first 100. Okay, now that we know this works, let's take it as comma separated values, CSV. Submit the query, and it will download it in a form that we can use on in Excel. And actually, when you do it for that, once you know it works, you might want to go and put like the top 1,000 and do it there. Okay, with that in mind, let's open this up in the spreadsheet. Now, when you open up a CSV file in Excel, it'll come up as a spreadsheet. Let me put it here. I guess I don't. Oh, no, I did it quick. Right, there's the CSV over my other screen. All right. You can, I would just say, save it as an Excel spreadsheet, Excel workbook, so that you can put the plots on it. Okay. Question in S.Z, what is Z? Again, S is the short name that I assigned to the spectroscopic table. Dot tells it what variable within that table are we looking at, and Z in this case means redshift. Notice that there are other meanings of Z in other kinds of tables, like the Z magnitude filter, which is a longer wavelength infrared filter. But in the spectroscopic table, it means redshift. And I'll show you how to find what you're looking for in each of these tables in a moment. Okay. And then what I do is I delete that first line, because if I want to do a plot of that versus that, the first line with other stuff there without a column heading properly messes up Excel. So we just delete that. Okay. And then for everything else, if I want to add on more data, I just copy and paste it to the spreadsheet that I've got. All right. So I've got those here. So now we can simply plot the axes that we need. Takes a little bit of time to get it looking right. You want to have your vertical and horizontal scales match. And you can just do that by expanding it or stretching it. See, if we expand it too much here, then the horizontal axis is very stretched out, but the vertical axis, the scale is different. And we want it to be this. We want the scale, the tick mark positions, to be as rectangular as we can get them. Okay. Now I did these diagnostic lines here, the KO1, KO3, and the sievert liner division line, just by plotting points. So I made a little list of some coordinates so I could copy and paste, pasted them in for X here, and then I calculated the function I need for Y. Like that. I will note that if you take them too far, these equations, these only work over limited ranges. Take a look at the graph to see how far over to the right you can go. And then if you wind up seeing it jump up, kind of like a tangent function would, where it goes infinitely negative and then comes back from infinite positive and then is over here, you know, you just went too far, cut off those last few points. That was just trial and error. All right, so I plot those. And now I know that my active galaxies are up here for this plot, up here for this one. Here are my sieverts, here are my liners. Okay, so what do you do with it? Well, once you have found these, the fact that we came up with the object ID, which you can click on copy here and you can do a search for that. And we've got the right ascension and declination. These are in decimal degrees, not in degrees, minutes, and seconds, but decimal degrees. And not in right ascension is in degrees too. It's not in hours, minutes, and seconds. And we've got the redshift. We can use that for some cosmological stuff. Okay, so once we've got this information, we can identify it in the Sloan database. We can, in fact, go to, let's see here. Let's take this one. We'll go to the Sloan database and we will search for that galaxy. So we're in the SQL search. Let's do a let's see here. Visual tools. I want the navigator. Okay. I put in that right ascension. Let's get the declination. There we go. So now you can find it. You see what it looks like. Now, I didn't look to see where this thing fit on the plot, but it looks like there is a fairly bright nucleus there. And we've got a spectrum here. Okay. Once you've identified it, you can do other things. You could take a look at the shape, the visual appearance. You can see if it's in a cluster or not. But what I'm going to recommend that you do for a project is that you identify your sieverts and your liners. Do it first for, say, low redshift, maybe below 0.1. And you're going to want to make that range of redshift be fairly narrow. At high redshifts, you can get by with a difference of like 0.1 in Z for your range. At low redshifts, you may have to go to a narrower range so that the distances are all pretty consistent. Because see, you're getting back apparent magnitude. And if you want to compare things at low redshift and high redshift, the apparent magnitudes are going to be just fainter and fainter for the high redshift ones there. You can't make that comparison. But your comparisons of magnitudes of the sieverts and the liners for any redshift bin will be pretty similar there. You can make a comparison between the two anyway. So what you should do is make a histogram of the distributions of magnitudes for the sieverts here and the distribution of magnitudes for the liners. My expectation is that the liners are going to be in fainter galaxies, but that might not be true. I really haven't studied liners. I work on sieverts here. And so I don't know what you'll find exactly. I'm sure that there has been work on this. I know there's been work on this. But take a look at low redshift. Do they have similar distributions of redshifts, or do liners stand out in one way or another? Next, go to a higher redshift, like 0.2, and see if there's see if the distributions are the same, or if you wind up, again, you're going to wind up, they're all going to be fainter at higher redshift, but see if the relative distributions are like they were before. And then finally go up to the highest redshift that you can. Now, I have found that there are no galaxies in the data release 16, which will fit the search criteria that I did here at a redshift greater than 0.4. Roughly 0.4 is the highest redshift that we have these lines that work out this way. So you can't go beyond 0.4 with this. But you can go up to 0.4. So like 0.3 to 0.4, maybe 0.35 to 0.4 might be your high redshift bin. And as I was mentioning before we started up here, for every 0.1 in redshift that you go out, for every 0.1 in Z, like 0.1, 0.2, 0.3, 0.4, up to about 0.5, you're looking backwards in time an additional 1 billion years, almost exactly. In fact, it's very close to linear for low redshifts. So you can see how much difference in cosmic time you're looking at, and you can see what effect did the evolution of the entire universe have on maybe relative numbers of sieverts and liners. Do you have more of one at high redshift and more of another at low redshift? And do their relative magnitudes change versus another? Are they indistinguishable at any redshift then? Finally, you could, if you were rather ambitious, you could track down what each of these, their images by going to their object ID, their right ascension declination equivalently, and you could download the images for them as a FITS file from Sloan with the data release here. You could do, let's see, that's interactive spectra and image mosaics. Go to imaging data. Slowly. And image files here. All right. Actually, it looks like, I guess, Science Archives server. I was thinking that the Navigate tool, you may still have a link to the image itself. In fact, probably you do. Let's see, if we want to go to this one here, we hit Explore. Oh, Explore. And FITS. And you can select which ones you want to get there. Okay, and if you're ambitious and you know how to run, say, GalFit, which is a galaxy shape fitting tool, then you could find out the change. You could find out whether sieverts are in one kind of galaxy and liners are in a different kind of galaxy, or whether they're the same, and whether there's a change over time again. So I will leave that here this morning. I'll take questions that you've got now.
Yeah, so actually we have covered GalFit. So, but we did it with HST data.
Uh-huh.
Yeah. So we have to handle the
You said you've done GalFit with HST data?
Yeah, yeah. And
okay.
we show them time and all also. So how would they have to do it with SDSS for PSF? Because the rest they know how to do it. How would they handle PSF?
How would they handle the SDSS?
PSF, yeah.
It would work pretty much the same way. The only real difference is that you're dealing with ground-based data, so you have the atmospheric effects that get in the way. But you can go to, let's see here, if I do R.
So, but then otherwise the way would be that use Dowfort and get a PSF, right, from Dowfort?
Yeah, you could pick a star in the frame to be your PSF, or I think you could just do a Gaussian model there. And yeah, that can be an issue, but there are generally some stars in the frame, and if it turns out, now the liners are not going to be generally not as bright, and you may not have to worry so much about a PSF. But the sieverts, some are going to be brighter, some are not going to be as bright, and you might need to deal with a PSF for that there.
No. So then you would suggest the Dalfort method of doing it? In the sense, look for a and
Yes,
characterize.
Dalfort would be very good for this.
Okay.
By the way, I'm noting here that I've just clicked on the one of the frames, and that downloads the FITS file. Notice it is a BZ2 archive compression. On the Macintosh, it automatically will extract that if you double click on it, but on Windows, you might need to look and see which software you need to unzip it. Let's see here. Bharjalala Sharma asks, can we play around with different ratios of elements instead of the ones that are used here? Well, actually, that might be a good thing to do. Now, but the thing is, you would need to know which class of galaxy you're dealing with before you plot it in a different format. So for something like this, TopCat, which I know that y'all have covered as well, TopCat would be excellent for using. In fact, for the plots that I showed you, the BPT plots, TopCat may be your better tool, because with TopCat, you're able to draw regions around your objects in your scatter plot and select just those, and it'll highlight. With Excel, you can do it, but it takes a lot more work. You have to put a lot of if-then statements into every single galaxy. I mean, you can copy and paste it there, but it's more of a pain to select them based on where they are in the plot, and then to know which row they are in the data table. So I'd recommend using TopCat for that. Now, once you've colored them a certain way, and you know, all right, these are my sieverts here. Now you've identified those. Now try to go plot them with different elements, different line ratios, and see if you can find a graph where they come out to be better separated. I should note one more thing there, that if you're going to play around with different line ratios, you need to know what lines they actually measure. So with that in mind, I have here, there we go. Well, let's see, it's in the, let's go search. Hang on just a moment. There is a link here. Here we go. The schema browser. Now, that's a lot of technical jargon, but what it means is that if you're looking for, say, the spectral lines, and I told you that the spectral lines were in this galaxy spectral line table, okay? That's either going to be what's called a table or a view. You just go to the schema browser, click on tables, scroll down. I don't see galaxy spectral line. Oh, I do see it, gal spec line. You click on that, and what you get is every variable that's in that table. And it says what the variable is, so the variable name, the type, so the data type. You don't really care too much about that. Oh, I mean, I guess you should. Data length, you don't care about that. The units, UCD, I'm not sure what that is. And finally, the most important thing, the description. So here, you get some, here's a O2 3726 equivalent width in angstroms, and it explains it's the equivalent width of that particular line. So you can just scroll through here. They have them in order of wavelength, and I think it's from short to long. And you can just see what other lines are available. So yeah, try that. Just make sure you plot them with the Lisa Culley division lines first, identify which ones you got for which, and then see how they wind up mixing. Make sure you color those points differently from when you play around with it. Other questions? You're welcome. should say also, if you want to play with some of the others, some of the ones that I used are called views, which is simply a kind of table that's made from other tables. So look in the tables and the views. Ooh, they've got functions. You can do all kinds of calculations on the data before you have SQL return the data to you. I did a logarithm of a ratio there, for example. All right, anything else? Okay. Any questions from you, Priya? All right. Well, everybody, that is it from me. So I hope that you've gotten something out of this one today. And if people have questions, then you're welcome, Telegender. If people have questions, you can send them on to me. Priya's got my contact information, and I think some of the rest of you do already too. But I'll be happy to answer them.
So thanks a lot, Tim. I don't see any more questions. Come on, are there any more questions? Please ask. Huh?
Okay, another question here. The equation of the line that separated the galaxies, how is it derived? Is it by using some curve fitting techniques? Tell you the truth, I'm pretty sure that Lisa had wound up just kind of drawing a line and said, oh, that looks about right. I think I'm exaggerating a little. There may be a way of, there are some data mining techniques where you can get the computer to fit, if you think that a straight line looks like it should be about right, you can get the computer to fit the slope and the intercept for you that way, in a way that will have the fewest misclassifications based on it. So there actually is an automatic technique. A lot of this you can do by eye.
Yeah, there's some questions on YouTube. Yeah, just read.
Where to find zero mag for SDSS?
But find zero magnitude.
And also the plate scale values.
Yeah, oh, okay. These are all input parameters which they need for GalFit, right? So they are asking about that.
Okay, so now what was the first one?
Zero magnitude. Zero magnitude, and second one is plate because they need it for GalFit.
Okay, the 0 point, yes. So for that, and I'll have to admit that Sloan is a little hard to find certain pieces of information, I've noticed. But if we go to, Sloan uses a kind of magnitude. It's not the conventional kind of magnitude, the so-called Pogge magnitudes, Pogson magnitudes. It uses an arc hyperbolic sine magnitude, arccinch magnitude. At brighter magnitudes, it gives you the same result. At fainter magnitudes, it's a little bit, it avoids getting blowing up at very, very faint levels. So let's go to data here. That's all Sky Server here. Hang on. Imaging. I think I've had it written down at some point, and in the observational astronomy book that I've sent you all chapters for some of the previous projects, in other parts of it, I believe I may have the Sloan's 0 point magnitude. Let me just see right here. Photometry. Because we do need that for the color magnitude diagrams as well, which we did back, that was last year, I believe.
Yeah. Yeah, that was last year. I was actually looking on the net for some Peng data itself, you know, the guy who wrote GalFit. If he itself has some, you know, he has examples on his website, right? Probably there should be something with SDSS.
Yeah, there may be. There is
But I'll
a
check on
place
that
where
one.
Sloan has it listed, but it is buried a little bit deeply on there. Actually, you know what? Let me just try something here.
And then do they need to worry about which data release? Has it changed with the different data releases? Or?
It's the most recent one is simply the most complete, but you can use older data releases and you'd get similar results. The newer ones, you'll just get more data. Flux calibration here.
No, I'm saying the values of these factors, but they have to.
Oh, like the 0 point.
0 point and yeah.
The 0, I don't think the 0 points.
Scale should be the same, but 0 point.
Okay.
Okay, so what we can do is, if you could, check up on that, and then I can put it on the website where the project is listed. So we can actually then even vary the GALFIT one in the sense that they can do it for SDSS as well as HST. Otherwise, they were doing HST till now. They can even try it with HST. I said,
okay. Looking up here.
Yeah, we have a galaxy morphology project which was proposed since the first this thing. Because we use that on a regular basis. But I'm saying that in that we can incorporate this SDSS one also. It was earlier mentioned only for HST. We can put it for SDSS.
I will note that if you look at something which is very small, very compact, or very far away, which will make it appear smaller, when you're dealing with, you really have to be careful to see if you're getting close to the width of the PSF, it will simply appear rounder and more like an elliptical galaxy, even when it isn't really. So that's something that we got to.
Yeah. So generally, that worry is not there with HST, right? So, but with
it's less of a problem.
Yeah.
Less of a problem, but again, if you get something that's so compact, it's close to the width of the PSF. Yeah, it'll still happen. It's just that the PSF is a lot better on the Hubble.
Yeah, obviously.
Yeah. Okay, I'm looking. I think that I found this here, and here we go. All right, I'm going to include this page. It's down. If you look for search on the word 0 on this page here. That's here. SDSS.
Yeah, you can share your screen also. Oh yeah.
And 0 points.
Okay. Great.
And it explains this the use of the arc cinch magnitude. But for things that are not extremely faint, it'll give you the same results.
Okay. Okay, fine. Yeah. So thanks. We can.
All right.
You're welcome. The relevant question. Yeah. What about other questions? Do we have any other questions from the others? I would like to, this thing that apologize to the people who are new. We obviously, since we did not want to repeat, we are not repeating whole things, but you all will have to see the old videos. Otherwise, repeating it doesn't make sense. So the ones who had a little bit of a problem in following, please try to see the older videos and you'll be better off. I think there's another question. Thank you. The session was interesting. Okay.
You're welcome,
Okay. Okay, fine. So we'll let you go. Thanks a lot. Thanks a lot, Tim.
Okay.
Yeah.
Bye, everybody.
Yeah. Bye.
Good luck with all of these.
Yeah. Okay. And everybody, do you all want a break or do we meet after lunch? Please write on the chat. Yeah, Tim, you can this thing. I need to, I had left the morning free so that in case you wanted to stretch it longer. Okay, after lunch is what people vote for.
Okay.
So that we meet at 2 p.m. Okay, 2 p.m. today.
Bye, everybody.
Yeah.
Bye. The presentation, ma'am.
Okay. Yeah.
When will be the presentation?
I don't know your name. Moto X4.
Ma'am, Sukhvinder. It's Sukhvinder. So I had a presentation today at 2 o'clock.
Yeah. So you'll do it at 2?
If you have your session, na machine learning.
Yeah. No. But we'll start yours. We'll do yours because yours are going to be 10-15 minutes, right? Not longer.
Yeah. It is only 10-15 minutes. Yeah, so, I will do it at 2 o'clock.
And then there were other 2 people who wanted to also do, right? What about the others who want to present? Do you want to do it now, Sukhvinder?
Now, ma'am, I'll take some 5-10 minutes. Then I can go ahead
No, then maybe we can do it.
because I have to log in from my laptop. It is in my
Okay.
laptop.
The other people were Bishal Panthi, who said he wants to present, and Meshwar Shivaji. Are these people there? Timing analysis of compact objects. Are there others who want to do it now, or Sukhvinder, since everybody, huh? She needs 10 to 15 minutes.
So, ma'am, we can start at 2 only. That will be fine.
Okay, fine. Then let's meet at 2. Okay.
2. Let's meet at 2. At 2 we'll start.
Okay.
Okay, ma'am.
Okay.
Thank you, ma'am.
See you.
It was
Bye.
nice.